Hello everyone, my name is Arohi and welcome to my channel. So guys, in my today's class I'll show you how to perform image classification using vision transformer. So I'll show you how to train your vision transformer model from scratch on your custom dataset. Okay, so let's begin. So the first thing is dataset. Okay, so I have a folder with the name of custom dataset. Inside it I have two folders, train and test. Let's open this train folder. So I have two different classes. So guys, whenever you want to work on an image classification problem, then what we do, how we arrange our dataset, how we prepare our dataset, we have a different folder for each class and the folder name will be the class label. Okay, so in my case, so I'm working on two classes, Daisy and Dandelion. So inside Daisy I have 200 images of this flower type, and inside this dandelion I have 200 images of dandelion. Okay, so this is my training dataset, and then inside the test dataset again I have those two folders. Okay, these are my class names, class labels, and inside this I have 77 images of Daisy, and inside dandelion I have 105 images. Okay, so this is how you prepare your data set. So in my today's class I am working on an image classification problem, and by the end of our today's class our image classification model which we are going to build using vision transformer will be able to classify dandelion and Daisy. Okay, so let's start with the coding part. So here you'll put the dataset, and now I'm showing you this code. Okay, this one we are training a model from scratch. So let's start, and by the end of our today's class you'll be able to get this kind of result: prediction, the name of the class, and the probability, confidence score. Okay, so let's start the code. Yeah, so first I'm importing all the required modules. Okay guys, before this also I would recommend you to create a separate environment. Let me show you the versions which I am using so that you can also have the same versions. So Python version is this, and then I have installed Torch. And this is my Torch version. Okay, so while installing this PyTorch you have to see if you are using CPU. If you are working on CPU, then you have to install the PyTorch which works with CPU, but if you want to use GPU, then you should have your PyTorch compiled with CUDA. So in my case I'm using this PyTorch version, and CUDA is 11.6. okay, so that's it. This is the only requirement before start doing this code. You need a Python, and on that Python you need a PyTorch installed. Okay, and then here I'm importing all the required modules, and in this line I'm just writing if CUDA is available, and then use CUDA, otherwise use CPU. Okay, now in these two variables I'm giving the path of my train and test data. So train data is getting stored in this, and the path of the test data is in this variable. Okay, now we need to create a data loader, right? Because if what we want is we want to load the data, okay, and then we can use it. Okay, so for that what I'm doing, I have created a function with the name of create data loaders, and here you can see in these two lines. Okay, when you will work on your dataset, what you need to take care, you just need to take care over here, this and this. These are the two variable names which are storing training dataset images and test dataset images. Okay, and these two variables I have declared over here. So if you are using some other variables for storing your training path and image dataset, test image dataset path, you have to provide those paths over here. Okay, and after that we are having a class names training data dot classes. Okay, so it will give you the folder names like Daisy and Dandelion. Okay, and then this function will load the training data, and this function is for loading the test data. Okay, so after this, here now what I'm doing in this cell, I want to resize the images to 224 into 224 size, and after resizing the images I want to convert those images into tensors. So that's what I'm doing over here. See, I'm resizing the image first and then I'm converting into the tensors. Okay, so now next step over here. Here I'm defining the batch size. I'm using 32 over here, but it again depends upon the resources. Let's suppose if you are getting some memory related issue, then you can decrease the batch size. Okay, so in my case I'm using batch size 32, and in these three variables, create data loader. Remember, we have this function above here, right? So using this function, we are having our training dataset, test dataset. Okay, and you can see the class names over here. Class name, inside this class names we are having these two names. Okay, now we have loaded the dataset. Now let's just check if our dataset is loaded properly or not. Okay, so for that what I'm doing, I'm just picking a random image, and on that image I'm just printing the class name and the image. Okay, so this tensor 0 means daisy class. If we have 1 over here, that means this image belongs to a dandelion class. So now our dataset is loaded properly. We can see we have the corresponding labels, images, labels. We have this properly. Okay, now from here the task starts. Till now what we have done, we have loaded the dataset. Okay, now when you work in Vision Transformer, the very first step is we divide the image into patches. Okay, so patches are small parts, small squares. Okay, you can see here, like for this input image, these are the patches. Now my patch size I'm using is 16 into 16. So in original paper, the very first paper of Vision Transformer, in that also author used the 16 into 16 patch, and Stride also used 16. So I'm following those parameters only to execute my today's example. Okay, so you can see if this is an input image, we have these patches. Okay, so now how many patches we are going to have? If our image size is 224 into 224, okay, and it is a RGB image, so now if you want to have a patch size 16 into 16, so we are going to have 196 patches. How? Divide your width of the image and the height of the image by the patch size. Okay, and then you will get 196. So you can see we have 196 patches over here. Okay, so we will turn our image into patches. After that we have to flatten the patch. You can see over here we have to flatten the patch, and before giving this data to the transformer, Vision Transformer, we have to convert our 2D patches into 1D vector, 1D embedding. So like this. Okay, so these all steps we are going to follow in this section. So I have created a class with the name of patch embedding. In this, the number of channels are three because it's a RGB image. Patch size is 16. Okay, so I've just told you that I'm following the original paper. 16 into 16 patch size we are going to use, so that's why I've written 16 over here. Now this embedding dimension, why I've written 768 over here? So means when you are going to have patches, okay, so we are going to have 196 patches. For each patch, our embedding dimension should be 768. How I came up with this number? Because 16 into 16, the patch size is 16 into 16, and it is a colored patch into 3. So 16 into 16 into 3 is 768. So once you flatten your patch, every patch should be this should have this 768 different tokens, okay, or elements. So this is what we have defined here. This line, see guys, over here I have used a conf 2D layer. This conf 2D layer will help us to provide will help us to divide the image into patches. So remember guys, in convolutional neural network also we use conv 2D layer. So what is the task of this conv 2D layer? We define the number of kernels we want to have, and we define the size, right? And this layer gives us those many kernels with the defined size. So using this con 2D layer, we are going to have our patches. Patches are like kernels filter size only, right? So in our case, you can say that patch and the filter feature map is same thing, okay? But what we are doing is, here the feature map size we are defining is 16. So we want a square of 16 into 16. So for creating a patch, we are using this con 2D layer, and we are defining it is a colored image. 3 means RGB image. Embedding dimension is 768 because we want to flatten our image in this size, okay? Kernel size, remember this is what I'm just telling you right now, a few minutes back only, that kernel size we are giving 16. That means we are going to have patches of 16 into 16 size. Stride, in stride also I've given patch underscore size, because patch underscore size is having the 16 value, and what it means over here is that I want to have a stride 16. Patch size is 16, stride is also 16. Okay, so when stride is 16, that means there will not be any overlapping when the sliding window will move from one place to another, and it will keep on moving. So at that time there will be no overlapping, because overlapping of the patches, because what we are doing is patch size is 16 and the stride is also 16. Okay, so this will create the image into, this will convert the image into patches. Now we have the patches, then we want to flatten them. So for flattening the patches, we are using a flatten layer. So all these layers are already there in PyTorch. We are just calling those layers as per our architecture, and we are performing the task. Okay, so after converting the images into patches, we are flattening them, and then we are using this forward function over here. What is the task of this forward function? See guys, finally when you will execute this code, there is a, you have to follow the format. Our output format should be this. Let me show you here. We want the output of this cell should be like this, 196. What is this 196? 196 are the number of patches. Over here you can see n means number of patches. So this, and then 768. What is this 768? When you flatten your patches, every patch should be one dimensional vector, and one dimensional vector or embedding, which will have 768 different values, right? So this should be the output. Now after these two steps, we are using this function, and over here you can see patches, flattened, and over here we are just converting the output which we are having over here into the format, so that we can have our output of this patch embedding like this. Okay, because this is how we need the desired output, then only the further process can be done on it. Okay, so this is important. So we are converting it into the desired output format. So that's what we are using over here. Okay, and forward method we have used over here is because we want to work for each patch now, so that's why this forward function is getting used. All right, so till now what we have done, we have an input image, we converted that input image into a patches. After that we flatten it, and then we converted into the format, the desired output format. Okay, now let's just check, let's run this class and check what kind of, whether we are getting this kind of output or not. Let's check it. So for that, what I'm doing is, this is just a function for random seed. Okay, now here you can see in this variable I'm calling the patch embedding class, this patch embedding class. Okay, and we are providing the input parameters. Channels are 3 because we are working on colored image. Patch size is 16 and embedding dimension is 768, right? So I told you how we get this. Now here you can see we are just passing, we are working on a single image. We want to check whether this class is working properly or not, so that's why we are working on a single image right now. So I picked the image, and then we are using the patch embedding, which is in this patchify variable. We are passing that image over there, and here you can see the output. See, before using the this patch embedding class, the input, the image is this. 1 means batch size 1 image, 3 means number of channel, and height and width of the image. This is how our input image is. After applying the patch embedding, you can see the output now. 1 means batch size, we used 1 image. 196 means how many number of patches we have, 196 patch. And how many different values are there in those embedding vectors, right? We flattened the patches now. 196 patches we have, we flattened them, and we have now embedding, right? So every embedding, for every patch we are having 768 different values. Okay, so this is what we want, this is our desired output format, so we have that. Now let's just see what are the different values are there in the patch embeddings. I'm saying that 768 values are there in every patch embedding. Let's see the values. So what I've done, see, I'm just printing this patch embedding image where I have applied the patch embedding class. So you can see these are the different values for the first patch. Okay, this is the 1D vector embedding of second patch. In the same way, we have 196 different patches, 1D vectors. Okay, and every vector have 768 tokens or 768 pixels. Okay, so our patch embedding is ready. Now our dataset is, now the images are ready. Now we can provide these images for further processing. Now what is the further process? You can see here that this class embedding is also used, and then we have positional encoding. Now these two steps are pending. Okay, so till now we have done till this linear projection. Now after linear projection, our task is to add class embedding, okay, and then to add position encoding. After positional encoding, positional embedding, we will provide that to the transformer encoder. That vector will go to the transformer encoder. Now let's do these two tasks. Okay, so in this cell here you can see, okay, so in this cell what I have done, this part you already know, patch embedding I have told you, right? To convert the image, patch embedding is the class which I have explained you, which will give you data in this format. Till now we have done this much, and the important thing is from here, these 4 lines will give you the class embeddings. Okay, so what is happening here, class token, how we are providing, we are using the parameter over here, torch.ones. Okay guys, over here I'm just showing you this function with torch.ones, but in my next cells I will show you how exactly, but how in actually we use it. Why I have used torch.ones over here, because I want to show you the kind of output we are going to get, and when you'll get 1 1 1 in every vector, so it will be easy to see the results. So that's why I've used this torch.ones. Just in when we are going to work on a in below cells, when we are going to use it in reality, over there we are going to use RAND. That's it. This is the only function. Torch.rand will give you a random values. Right now I'm using ones. Torch.ones, batch size 1 and embedding dimension. How many, what is our embedding dimension? 768. Remember, 16 into 16 into 3 is our embedding dimension. Okay, and here I have printed the shape of this, and then we are here in 8th step we are using the position embedding. here we have used the class token embedding. After that we are using the position embedding. In position embedding also we are using this, okay, torch.ones. Now let's print. Here you can see at the very first step our image would be of this size, right? And then we convert it into a we are providing a batch, and then after patch embedding you will get this kind of output, okay, 196 patches of this size. After that we added a class embedding, and you can see what we have done in class embedding. The shape is, we have added 1 in all these 768 all these 7 over here. You can see the output, see 1 here, right? So this thing is added. Earlier it was not there. If you'll see the result above over here, when we check the output of patch embedding, over there we are not having any ones on the top, because till now we haven't added the class embedding, okay? But over here when we have added the class embedding, we have ones on the top. Why we have ones on the top? Because over here we have mentioned torch.ones, okay? But in reality, in our next cells, I'm going to use torch.rand over here. This is just for the display purpose, so that you can understand what this class embedding is doing and where this value is going to be added, okay? So now we have position embedding and class token. Everything is added now. Now this is the our transformer encoder. Now we are going to build that. Now we will provide our vector embeddings to, now we are at this place, okay? Till now we have done the code till now. Embedded patches are ready now. Now we will provide it to normalization layer and then the multi-head attention layer, right? In this way we are going to build our code further. Let's see how to do that. So in this cell I am building a multi-head attention block. This is the main thing in transformers, the self-attention task. So that is what we are doing here. Created a class. In this first, okay, this is clear 768 embedding dimensions. Number of heads 12. This is as per the again the original paper vision transformer. Over there they have used the number of head 12s, but you can change it. Attention dropout is 0 right now. And then normalization layer. How we can create the normalization layer? Using this, okay? So you can see in this architecture, first thing is normalization layer. That's what I've done. After that we are using a multi-head, creating a multi-head attention. So next is multi-head attention. We are creating that, and we are providing the embedding dimension. Number of heads, embedding dimension is 768, number of heads are 12, attention dropout is 0. Batch first is true. That simply means, does our batch dimension comes first? So true means yes, our batch dimension comes first, okay? So normalization layer, multi-head attention layer, and this forward layer is just a method to pass the data through the layers, okay? So here you can see query, key and value. So guys, when we use the concept of self-attention, so there is a thing that for every for every 1D vector, for every patch you are going to have a query, key and value. And what is query, key and value? If you want to understand, then I have done one video on transformers. In that I have explained this with example. You can check over there, okay? So yeah, query, key and value. And then this is what, this is how you create this multi-head attention block, okay? So now what we have done till now, we have done this, okay? Now next thing is MLP block. This MLP block, normalization code is same. Whatever you have written over here, the same thing will come here. So now after that we have this MLP block. Now we are writing code for this layer. Yeah. So here this is our MLP block. Again you have to provide the embedding dimension, MLP size. So 3072, dropout is this. Again we are using the normalization layer because before using MLP there is a normalization layer, so that's what we are using. And then MLP here we are creating a multi-layer perceptron over here, right? Input features we are getting from here, and then just scroll down and you can see the entire MLP architecture over here. Okay, and then forward mass, again this forward function is used to pass the data through the layers. Okay, so this is our MLP block. So what we have done in this, we have just used a normalization layer, and then we are using we have created a MLP, a small network, multi-layer perceptron network. Okay, then after that, once you have, till now what we have done, we have the code for each of these, we have this code, we have code for this layer, but now we have to put all of these layers together. Okay, so that output of this becomes input to this, means we have to follow this sequence to process the patches, right, process the embeddings. So till now we have a separate code for each layer. Now we'll combine it, so in order to get this whole encoder working. So how we did that, we created a class transformer encoder block. In this class now I'll use this MLP block and this multi-head attention block together in order to make a transformer encoder working. So you can see here that here we are defining all the important parameters which I have told you above also. Then we are using multi-head attention block. What is there in multi-head attention block? First the normalization will work and then this layer will work. Okay, so that's what happening. We are calling this, that means normalization and the multi-head attention code will work. After that we are calling this MLP block, and in MLP block also we are using normalization layer first. Okay, where is this? This is the MLP block. We are using the normalization layer first and then we are using the MLP. So that's what happening. Okay, and then forward means it will, you know, process all the layers. It will pass the data through the layers. So now our encoder, transformer encoder is ready. Clear? So now next thing is, just if you want to see the summary, means how the summary looks like, then you just need to, we are calling a transformer block encoder block class here, and then we are using this, and then you can see the summary of it. Okay, so now our transformer encoder is ready, patch embedding code is ready. Now we have to put all these things together, patch embedding and then this transformer encoder and then the final classification layer which will make our classifier. We have to put all these codes together now. For that I have created a class, this VIT. Okay, and these are all the important parameters: input image size, channel, patch size. If you want to work with some different patch size, then you have to change this value. But remember, if you are changing this value, you have to take care of this value also. Okay, the patch size, whatever your patch size is, suppose in our case 16 into 16 into 3 is 768. So if you are using some other patch size, you have to adjust the value as per that. Okay, so these are the all important things. Now this line will tell you how many patches you are going to have. So how many patches we are going to have? 196 patches. And then here this will add the class embedding, means it will add the ones. Okay guys, here you can see I'm using torch.rand, so random number. So remember, in my upper over here where I have explained you this code, here we are getting 111 like this. Okay, why? Because in this class embedding I was using, here class embedding I was using torch.ones, and this is just for display function. Okay, so we got all the ones like this. But in reality, when we are working on a vision transformer, what we have done, we are using torch.random number. So what happens in machine learning or deep learning? What we do, we start with some random value and slowly our algorithm learns and it came up with the right value, right? So that's what we are doing over here. So this is our class embedding, and then this is the position embedding, because we give all the data to transformer at one time, so transformer don't know which patch comes before or which patch is the second number, which patch is the third number. So this position embedding will help in that. So position embeddings are also added. This is the patch embedding code. This will convert your image into patches and then 1D vectors, and then we'll add this class embedding and position embedding to it. After that, here transformer encoder block. This is the encoder of the transformer, remember, where this is the class we have made. Here we made this code over here, transformer encoder block. In this we have called this and this MLP block. Okay, so this is the encoder. So then we are calling this transformer encoder. After that, this is our final layer which will classify the image. So what you need to do, you just only need to take care of num classes. Num classes will be the, in our case we have two classes, so output class will have two neurons. So this is our final class, our classifier, and forward method is this. Okay, so this will just help you out to take your data through the layers. So now our vision transformer class is ready. Now we want to train our model. We want to train our data set using this class. Okay, so that's what I'm doing. I'm calling that with class over here, and then here you can see engine.train model VIT. This we have over here, and then we are loading our training dataset, test dataset, optimizer we have defined here. You can change these values and you can see how it affects. I'm just training my model for 10 epochs. Okay, you can increase it, device, if CUDA, if GPU is available it will use CUDA, otherwise CPU, and I have trained my model for 10 epochs. Now you can see the accuracy is this 40% from here, then we have this much, and loss is also not good, accuracy is also not good. Why it happens is because we trained our model from scratch and we trained for very less epoch, and dataset is also very small. Okay, but let's just see, if you want to plot the curves, this is our loss curve and this is our accuracy curves for all the 10 epochs, and let's make a prediction. So this is how you can make a prediction. Here this is our image, and then I'm using this function, and here you can see calling the model, image path, and the class names, and you can see our algorithm is predicting class name is this, probability is this. So but guys, this model is not performing well because because we trained it from the scratch and the dataset is very less, and we trained it for very less epochs. So now in my upcoming class I will show you, we will work on the same dataset, we will train for same epochs. The only difference will be that we will use a pre-trained model. Okay, we'll take our pre-trained model and then we fine tune it, we'll change the classification head of that, and then we will see how it performs. Okay, so that way we can improve the accuracy, we can improve the loss, and we can also, our predictions will be better that way. Okay, so in my upcoming class, in my next class, I'll show you how to use a vision transformer pre-trained model on a custom dataset, and then how to customize it, how to make our model better using the pre-trained model. Okay, so this code, the link is given in description section. You can try this code, and guys, if you like my video, please like, share and subscribe my channel. Thank you for watching.